Okay, so welcome to Victoria Probability Seminar. Today our speaker is Associate Professor Andrea Collevecchio, and Andrea is, like we discussed recently, is Director of Research in the Monash Data Future Institute, but also he is an Associate Professor in the School of Mathematics of Monash University. So Andrea did his PhD a long time ago in 2004, and after that he had a couple postdocs and some positions in, for example, in Venice, and then from Italy he moved to Monash, where he is probably happily stay here. Andrea is well known for his research in areas connected to reinforced processes and large deviations, and he is interested in many topics in probability analysis and also the connections to mathematical physics. And I always enjoy Andrea's talks. They are very interesting and topics very often quite unusual. So Andrea, you are very welcome.
Thank you everybody. Thanks for the invitation and thanks for the introduction. It's very nice. And yes, I've been here for a while and I'm here to stay. I really like this place, and I'm going to talk today about random walks, but a special kind of random walks. This is based on joint work with Minh, Nguyen and Stas Volkov. And but before I start talking about what we have been doing recently, I think I would like to spend some time to review what has been done since the genesis of what is called reinforced random walk. And even before, if you think of random walk themselves, when you teach it, most probably it's tempting to use the metaphor of the drunk person walking at random and not knowing where to go next. So it's Markovian process in the sense that the future, given the present, is independent of the past, right? The next step is independent of whatever you've done before. And this could be only explained on a basic level, saying, okay, this person, this particle is completely drunk. But what we're going to study today, I mean, to analyze today, or to discuss today, is a different type of walk, in the sense that I think that it's good to keep in mind a model where, or a situation where you are exploring a new city. You are new there, and somehow if you are unfamiliar with what is there, you have the tendency of choosing the places that you already know, or at least it's what I do, and maybe too naively, and think of something that you not only have this preference, but you reinforce the sides or the edges, if you think of the street as edges, that you already traversed in the past, that you already know. And the more you do that, and the more likely you do it in the future, if you are in that location. But we need to, this is very naive description, we need a model. And the first thing that we have to do is to transform the city itself into a graph, something that we can play with. And instead of the streets, we have these nice edges, and maybe even, I mean, what I'm going to focus mostly during the talk, at the beginning of the talk, is the simplest possible graph where these things are interesting, and this Z itself. But in the back of your mind, also for the second part of the talk, you can think of a grid, and mostly an infinite grid. The walk will interact with the graph in a certain way. Or if you want, you can think of it interacting with itself. So as I say, it's going to be non-Markovian. It will learn from the past, and it will learn in such a way that it will reinforce its experience. It will reinforce vertices or edges that have already visited before, and it will reinforce it depending on how many times have been visited. But let's discuss the model now. It's you just have one parameter to keep it easy, and the parameter itself is a function. is a function W, and we are going to use this function all over the place. It goes from 1 plus infinity, positive. It's the only requirement at this stage. And we focus now on Z, the graph obtained with the integers. And to each edge of this graph, we're going to assign an initial weight 1. So I'm not sure if you can see this. I think it was poorly scaled. But suppose you start from the origin 0. Initially, you have all 1s. The random walks we are going to talk today only jumps to nearest neighbors. So from 0, it must go either to -1 or 1. And the very first step, it chooses uniformly at random, 1/2. With probability 1/2, for example, can go to 1. If this happens, you change the graph. Not the edges, not the vertices, but the weights. In this particular case, we're going to change the weights on the edges. And you increase by 1 each time you cross that edge. So now you are in the situation, the actual position now is 1. You just traverse the edge connecting 0 to 1. The weight becomes 2. And now you ask yourself, I have 2 options next step. Either I go back to 0 or I go to 2. What's the probability you go back to 0? Well, the function W now plays a role. W2, so what you read 2 is what you read above the edge, rescaled in such a way that you have a probability. And of course, this is why you need positive function there. So this becomes a probability. Could keep going. Now, if that happens, that you go to 0, the actual position now is 0 at time 2, that weight becomes 3. What's the probability you do something new, that you go to -1? Well, depends on the weight that connects the edge, the new edge, the edge that you didn't traverse so far, and properly rescaled. So it's this ratio that you see at the bottom of the page. This is an edge reinforced, is a general one. It wasn't the original model. The very first model was where a specific W was chosen and was the most popular, I mean, the most natural, if you want. And is when W is the identity function. And if you want, you are increasing, there is the linear case. This was studied by Coppersmith and Diaconis, and this is the most cited, I think, unexisting paper that I ever heard of, because this paper does not exist, I think. I never seen it, and it seems, from what I heard, it's not that. But I would say in a sequence of seminars, and they had, or maybe I'm wrong, maybe it will come out, but I never seen it. And I also cited it, because it's there. And it's what they did was to study this work, I think, in general, in the sense that I will introduce later a few quantities. They could describe the local time of the random walk, the local time profile, the distribution of the local time profile. It is so-called magic formula. I'll go back to it later. But on Z, things get easier. You can study the walk that looks a bit complicated locally. So you just fix your vertex X and ask what happens at X. The first time you reach X, if X is positive, if the origin was here, the first time you reach X, you must traverse the edge. There is, of course, a typo here. You must traverse the edge connecting X minus 1 to X. So the original weight.
Andrea, could you please zoom out? I think we are missing part of the picture. Yeah, thank you.
Then what you see is different from what I see.
Yes, maybe.
Yeah. You see the whole picture now?
I see the last two lines now. Thank you.
Okay, good. It will come later anyhow. So when you reach X the first time, the weight of the edge connecting X minus 1 to X is 3. And I say something silly, it's not. It's actually going to be 2 here. My apologies, I need to update these numbers. It's going to be 2 because you cross that edge once and the initial weight was 1. Okay. Now, I wrote it correctly below. Suppose you traverse that edge at the first jump from X is 2X minus 1. So you reinforce by 1 by the time you do that. But then you have to come back to X. So this is the original 2 and you add 2. This is the second time, if it ever happens, that you go back to X. And you can keep going. Maybe here is correct. So this is 4 and this is 3. If the next time you go to X plus 1, if you come back to X, you must go through the same edge. So there are no cycles here. If you go, if you exit in one direction, you have to re-enter from the same. So the jumps from here is a Polya urn in the case of linear reinforcement. It's a Polya urn in the sense that each time you pick up, initially you have 2 balls of a certain color corresponding to the left edge and 1 ball of the other. Each time you pick the ball, you put it back together with 2 new balls. It's an exchangeable model. And you can study this by saying, okay, this is a mixture of beta with a certain parameter. It's beta 1, 1 So this becomes a random walk in a random environment because you just have to attach once and for all a random probability to each vertex and just get started. Now, you can think of it as something very specific to trees or anyhow, in this case, Z. It is a bit more general than that, in the sense that if you are on a finite graph and you run the same process in a linear fashion with a linear reinforcement, then is a mixture of reversible Markov chains. It's a very nice, it's a very nice generalization of the definitive here. Well, what happens if W is not linear? That's what I would like to discuss next. The same representation in terms of that graph that you asked me to zoom is the same. But the urn that is associated to the vertex X is not a Polya urn anymore. The urn will look like you start with 2 balls of this color and 1 of this. Okay, the probability to pick a black ball now is W2 divided by W2 plus W1. So if W is the square function, it's 4 divided by 5. So you see, you give a lot of preference to the black one. And if W satisfies the condition that I'm going to identify as stronger reinforcement, if this condition that W grows very quickly holds, then, and the random walk is still defined on Z, then we have this nice theorem. It localizes on exactly this. In the urn that you consider, from a certain time on, you just pick 1 color. The other color is picked only finitely off. If you want to translate this into the random walk associated with the W, the reinforced random walk, this is equivalent with a small extra work of the random walk getting stuck on one edge. In other words, the random walk will visit only 2 vertices infinitely often. Again, in terms of the urn, only one color survives in the sense that one color is picked finitely often. In terms of the random walk, and I remind you, the urn is just a tool for the random walk. Two vertices are visited infinitely often, and the rest is not. This is a theorem of Burgess-Davies, but as he acknowledged on his paper, he had 2 proofs essentially. But one proof was extremely elegant, and he put it in the appendix, and it was due to Hermann Rubin. And the Rubin construction now analyzes, I remind you, the random walk is something. The random walk can be studied locally. The urn does this job, tells you the behavior locally. So let's focus on the urn. We have 2 colors, red and black. And instead of analyzing this discrete system, the answer to the question, what happens to the urn, comes fairly easily if you embed this discrete process into a continuous one that seems to have nothing to do with it. You consider 2 sequences that are independent of each other, composed by independent random variables, so you have all the possible independence here. And these are exponentially distributed. Why exponential? Because we're going to use the memoryless property. You assume that Ri and Bi have the same expected value. And this expected value is 1 over Wi. Now, the first line that you see here, not sure if you can see the whole picture. I think so. This is B1. The second interval time is B2. So the time itself, this is the interval time, is the partial sum of the 2. And you keep going, and you will have an accumulation point if the sum of the Wi is finite, because the expected value of that sum is finite by assumption. You can do the same with the red, and then you overlap the 2. When you overlap the 2, you will see that if you create an urn like as follows. Each time you observe this symbol, you add a red ball to the urn. And then you freeze the system. You put the red ball and you continue reading on the line. And you stop when you see the next symbol. It's this. You add the black ball. And you keep going. Using the memoryless property and the fact that you can understand how the probability, you can compute the probability at one exponential is less than the other. Is simply the ratio of, is the parameter of that exponential of the other, actually, the scale. Making that computation, you understand that this is exactly the initial urn. It's just the narrative is much more complicated. On the other hand, now things become easy. Why? Because the accumulation point in the first line is almost surely different from the accumulation point in the second line, because you have independence and they are absolutely continuous, right? They are continuous distribution. Being independent, the probability that they are equal to each other is 0. So if one accumulation point comes before the other, and when you detect it in the model below, because you pick infinitely many of one color and finitely many of the other. So I've been a bit rushing on this, but I find it an extremely elegant proof, which can be generalized a little bit. Unfortunately, it's not so stable if you change a little bit, if you make this ball interact a little bit. If the independence drops, you are in trouble. I hope there are any questions about this. Please feel free to interrupt me at any time. Another version that is quite popular in the literature, but is much harder to study, is when instead of reinforcing the edges, you reinforce the vertices. Still Z. You move to nearest neighbors. You reinforce the vertices. Initially, you give weight 1 to each vertex with possible exclusion, and just put 2 there at the origin. The first step, again, you don't care. The very first step is uniformly at random between -1 and 1. But if you go towards 1, you increase the weight by 1. It's very similar to the model before. As you can see, the probabilities are very similar. Now is the probability, if you are in this configuration and you are at 1, the probability to move at 0 is W2 divided, rescaled by W2 and plus W1. Very, very similar model. The problem here is that you cannot study locally. You cannot decouple what happens in a region from what happens a little bit around it. In fact, the results here are completely different. So it was studied by Pimanton, I think in his thesis, and then in a sequence of papers, Pimanton and Volkov had very appealing conjectures. And the conjecture was that this walk will get stuck in the sense that the number of vertices that are visited infinitely often is exactly 5. This was actually proved by Pierre Tarres. I think it was 2004, and it was very nice result. It's extremely nice if you think also what happens in the boundary of these 5 points. Only 3 of them receive a positive proportion of time. The local time divided by t, by the time that you run the walk, is positive. The boundaries one, they grow logarithmic in time, and so they do not appear if you rescale. And it's a very nice result. And then its methods also very appealing, and people started generalizing this. So the 5 points, how can we push it? I mean, if we reinforce a little bit more or a little bit less, what happens? If you reinforce a little bit more, but not too much, so you are not in the strongly reinforced case. Bodemar, Shapiro, and Singh proved that if you still reinforce more, much more than n log n, but still not too much, in the sense that the sum of the reciprocal is infinite, then you get stuck in exactly 4 points. And they gave nice description, and they had a very nice result on Z. That is, no matter what you do, what W you use on Z, you will never get stuck on 3 points. Now, I know that this is 4, 5, 3, but no matter what, never get stuck in 3, on 3 sides. And this takes us to what I consider an intermediate model, which is the one after 30 minutes of talking that we're going to discuss. And is the one that with Minh and Stas we start. So it's called the Vertex-Reinforced Jump Process. Actually, its genesis is a bit peculiar, because I think it was conceived by Wender and Werner, but I don't think he wrote a paper on it. The very first 2 papers were by VRJPs and Stas Volkov. They studied it first on essentially on Z and then on trees. And the definition is the following. So you have to keep in mind a kind of Poisson process given the past. No, not really. It's locally, given the past is locally Markovian in the sense that, yeah, let's put it in that way. If at time t, you condition on the local time profile that you had in the past. By local time, I mean how long have you been in one site? And you ask what happens in a h unit of time between t and t plus h, where h is small. What's the probability that you jump to x plus 1? It's given by the usual function that we have in mind, computed in the local time at x plus 1, times h. So you can think of jump. That is the rate. But of course, the rate changes and changes very quickly because you update local time. So strangely, this is much less natural than the previous two processes. And its level of complexity, in my opinion, stands in between. It's a way easier, it's possible to study this process using the, I mean, it's approachable, whereas the vertex-reinforced, I think, in my opinion, is much harder. But after studying, so they introduced this model, they studied, I also studied this in my thesis, and I thought of it in separately from this. And I remember my supervisor was telling me in the long run, this should be like a random walk in a random environment on set or on trees. And he was right. He was very right. And I realized this in 2015 when I saw a very nice paper of Pierre Taris and Sabot Taris paper. The case Wx equal to x, the linear case of this complicated process, is actually after you massage a bit, you remove some, you give random initial weights and you perform a time change. That is a linear reinforcement model. This model includes the original model of linear reinforcement, the one that Coppersmith and Dicom is. Now, we are not going to focus on the linear case, but it's extremely important, and it's linked to a model from mathematical physics, which I'm not going to discuss given my ignorance in the field, but it's the supersymmetric Sigma-Model. And thanks to this new connection, they were able to prove some deep results on Z2, ZD. We focus on a different case. If you want you can think of it for alpha very close to 1, perturbation of the case before, but we focus on power functions, which are strongly reinforced. So alpha is larger than 1. And in the next part of my talk, what I'm going to do is to discuss this behavior, but on general graph. And that's the novelty of this talk. So what we're going to do is to check what happens on graphs on ZD, but can be anything. And as long as you assume that the degree is bounded by a constant. I think I'm going too fast also because I'm almost finishing my slides. So I'm not sure if I'm going to have a very short talk. So what did we prove is the following. And this is based, it's a sequence of paper actually. I'm just mentioning the very last one with Minh that we are about to finish and submit, but it's based also with joint work with Stas Volkov that we did a few years back, a couple of years back. And if under the assumptions above, no matter what is the graph, bounded degree, you have that with probability 1, there exists one vertex V such that the local time at V, let me use a different notation. I use LV infinity as the total local time, is equal to infinity. So there exists one vertex only that has unbounded local time. Of course, this is a nearest neighbor process, so it still has to jump. The vertices that are adjacent to V are visited infinitely often. But their local time is finite. The process accelerates very quickly there. And finally, for all the other vertices that have a distance at least 2, graph distance at least 2 from V, you only have finite local time. So it's a very strong localization. And as you can see, it's the local time at the neighbors of V is random, of course. So there exists a random vertex where this happens. And of course, I do believe that there is some kind of monotonicity in the distribution because, of course, the origin, the starting point should have some kind of preference, but I think also depends on at least on regular graphs, it should be true. But this is the main result. Any question about it?
So Andrea, it holds for any alpha.
For any alpha larger than 1. So this is important. It does not hold for alpha equal to 1. So for alpha equal to 1, you do not get any of this type of localization. And for alpha less than 1, neither. This work is very close, even though there is a vertex reinforcement, is very close to the edge reinforced. And both can be studied locally, and both do not localize if the sum of the reciprocal of the weights W is infinite. So if you are in the weak reinforcement regime, they do not localize. They localize with probabilities.
A very stupid question. Does the graph need to be infinite?
No.
Okay.
It's not at all a silly question. Actually, it's very hard question. And I'll tell you why. If you make a step back for edge reinforced, but very strong W, on infinite graphs, you can use a Borel-Cantelli argument that each time you are in a new territory, you have a possible probability to get stuck on an edge. And you can prove very easily that get stuck on an edge on any graph with a decent degree. On finite graphs, it was extremely hard to prove. It was proved in a very beautiful paper by Codina-Cotard and in general. I mean, there were a sequence of papers by Vlada Limic, Pierre Tares as well. And then it was settled completely using an inequality, a noble inequality by Codina-Cotard and the Blenataka. And it was important for the finite graph because on the finite graph, you don't have regenerative situations where I'm in this situation, I have positive probability that something happens, is independent of the past, and I can do that. On finite graph, you don't have that. So your question, yes, it's very pertinent. There is a difference, but the method, as I'm going to explain, works also for finite graphs. So you don't need that regenerative structure. And the finite graph part is the hard part. Any other question?
Andrea, maybe it's naive or maybe even not correct question. So yeah, this is like existence theorem, but say you have some starting point. Can you tell something about, say, for some regular graph or whatever, about distribution of distance from the starting point to this vertex V or something like that?
You can tell something in the sense that suppose you fix the graph and suppose that this graph, for simplicity, is Z itself. Okay?
Mm-hmm.
I'm going to show you that not the location, the distance. I'm going to show you an estimate for the tail of the position of this vertex V. Mm-hmm. And by tail of what? The distance of V from the origin. Mm-hmm. Yes, we did.
Okay,
by the way, another question I have, is this process exploding? I was asked this question a few years ago. And it's not, by the way, it's well defined in the sense that there is no explosion. Of course, the result tells you that because if you have one vertex that has local time infinity, it cannot explode, but it's also part of the result. Mm-hmm. Okay, so any other question? a little bit of who are the people who studied nonlinear VRJP? So beyond the, I told you more or less why, at least in my opinion. I find it interesting by itself. It's an intermediate model between the two and captures many things. The nonlinear part is, VRJP is more general than edge reinforced, right? It can still be studied locally. The first two people that I know that studied this were Minh, Nguyen, who is at Monash, by the way, and Olivier Raymond. And they had this very nice paper where they studied on the complete graph. So paradoxically, I've been telling you that graphs with cycles are difficult. They succeed in doing it already but they could use a technique that works for the complete graph. So the complete graph is more or less urn itself with many colors. And they use stochastic approximation. Their method was relying on stochastic approximation. Then Minh came to Monash. So together with him and Stas Volkov, we developed developing a different methodology relying on martingales. We could prove something on Z. Do you remember where I say that vertex-reinforced on the walk does not get stuck on 3 points? Well, VRJP does. And it does as long as you have that alpha larger than 1, but it's a bit more general than actually it's technical class of reinforcement, and I'm fine to consider just power functions. And it gets stuck exactly on 3 points. And only 1 point, the middle one, receives an unbounded local time. The other two have bounded local time, even though they are visited infinitely. And I'll answer your question, Andrea. Be patient in a moment about the distribution of the position, at least here. But this can be generalized to other graphs, as long as you have some kind of regularity, at least. Actually, you don't need that either. I'll tell you more in a moment. And yeah, so we succeed in doing this in 3 points. Then in the back of our mind, the natural question, which is also asked for other models, is Z is a kind of easy. Let's have a general ZD maybe. And we succeeded. Actually, once you try with ZD, the method is the same for any graph with cycles. And we did prove the generalization on any graph, as I advertised before. So the proof, martingale, in the sense that you start with a process that is not a martingale, that T is the difference. So I'm not sure if you ever seen the so-called Harris martingale, where you take the sum of the reciprocal of the weights. In this case, the weights are those reinforced. You take. So in this case, it's very similar. It's the integral between 1 and the local time. First of all, sorry, I should emphasize that the first analysis is when your graph has only 2 vertices and 1 edge. And we label 0 and 1 the vertices. For VRJP defined on this object here is quite nice. It's not a martingale itself, but it's a semi-martingale in the sense that it can be decomposed into a martingale, not local, actually a martingale, and something of bounded variation. Okay, so this is a bit technical the way we do it, but it's fairly decent object. It's the difference of 2 integral and the limit of integration are random. This limit here is the starting point. Initially, we give weight 1 to each vertex. This is a semi-martingale, and we prove, and this is hard, it's technical part of the paper, that does not converge to 0. Can converge, it will, but does not converge to 0. But if it does not converge to 0, it means, given, I remind you that we have this condition here, we are using power functions that are fairly strong, then if it doesn't converge to 0, you cannot have both local time going to infinity, because otherwise it will converge to 0. Okay? Now, as on Z, we can study things locally. This already gave us a boost on Z. Because on Z, you can study things locally because, you know, if you go out in one direction, you have to re-enter from that direction. And the definition itself of the process involves exponentials. The local time grows exponentially. So you can use memoryless property to say that what happens to the right does not affect what happens to the left. That's a very nice trick that I'm going to describe a bit more next. When you apply this on graphs with cycles, so on Z2, ZT is still useful. It's a bit more subtle to explore its properties, but you still have a decomposition and you still have to analyze the matrix. And that gave us the result. This allowed us to compare the behavior of the local times at two adjacent vertices. And this part, which is very technical, in my opinion, is what we use to analyze what happens on finite graphs. But why can we actually focus on finite graphs? And this now gives you an answer to your question, Andrea, I hope. Fix a graph, a subgraph C. And forgive my, suppose this is C, okay? And I highlight now those vertices that are at the boundary of C. And I ask, so these vertices that are highlighted, I call this C, and the vertices that are highlighted, I call them the boundary of C. Then I ask a simple question, the local time of the process at the boundary C, it means the sum of the local times at each of the vertex, by a very special time. The special time is the exit time. The exit time. I call it S here in the slides. Means the first time you move out, you go outside. I remind you that this graph is a subgraph of G. There is a way out here. Maybe some of these are no way out, but I only consider the ones that have an edge connecting to the outside, right? So each of them could be potentially the way out from C. I look at the time when I jump out of C, and I count the local time. I measure the local time at the boundary. Now, as I said, this is a kind of Markovian process if you look locally, right, at small jumps property. And I know that the local times here are 1 because they have been untouched. The origin is somewhere inside this vertex. They have been untouched. It's the first time you, the origin is inside C. I should have said it before. So the vertices that are out have never been visited. So you just look at the small, each time you are at the boundary, you have probability that to jump out that is at least, in a small interval, at least 1 times h, right? If you just look at the time you go out, you can see that this is stochastically smaller than an exponential with parameter 1. If you do this on Z, and you ask yourself, okay, this is minus 100, this is 100, what's the local time here? Okay, this local time is stochastically smaller than exponential. I jump here, and now with the analysis before, you have a positive fixed probability to get stuck here, independently of the past, because now you can decouple from the past if you can control this local time. This means that the tail of the distance, as you asked before, of V, the chosen vertex with the origin, is exponentially decaying. And you can give this upper bound. You have essentially each time, to make it, this is a success if, for example, the local time of the exit is less than 1, the total local time. Doesn't matter where you exit, local time is less than 1, then you here. This is, you can control this because it's 2. You have an extra exponential here, and you have a positive probability to get stuck there because it doesn't depend on this. And then you have a regenerative structure at distance 1. It means that you have an exponential decay. So you can control that one. Anyhow, what I want to emphasize very briefly, because from having too much time, I'm running out of time, is the so-called restriction principle. You can use either the construction itself of the process or the memoryless property of the exponential to be able to say that what happens in a small region is independent of what happens outside. This is called the restriction principle. It is satisfied also by the first process, the edge reinforced. It is not satisfied by the vertex reinforced. This allowed us to say that you can focus on finite subgraphs and then analyze those. And this is it. This reference is highly incomplete, so my apologies, but I invite you to give a look to these papers and the references there. And I mentioned many other papers during the talk, and I'll take your question.
Okay, thank you, Andrea, for interesting talk. So now we have time for questions or comments. Please unmute yourself and ask your questions.
Andrea, thanks for the talk. A silly question again, perhaps. What if you have got 2 working particles? Did anybody look at this? And if yes, are there any new phenomena that can occur?
So yes, and it's not silly. So first of all, why we look at it? There are many algorithms that look at interaction between particles, actually. And it's natural that particles interact. Think of ants that leave pheromone, right? So they have to interact, and they reinforce the path using this pheromone. Who studied that? There was a thesis of a student of Pierre when he was in Oxford. I'm not sure if this thesis has been published, and it was 2 particles with linear reinforcement. And then we had a preprint with Kais, but there was a gap. Kais, Minh, and we're working on it. So we are thinking of the stronger reinforcement there, and with actually it's also very general reinforcement and 2 particles on the finite graph. My point is it's much harder because of course you have to see the interaction between the particle is quite attractive too. I mean, is it true that they all get stuck on the same edge or they all get stuck on an edge? Because even one can perturb the narrative of the other, right? It's very difficult. It's very interesting. I hope I answered. These are the only 2 that I know, but I might miss something.
Andrea, is there any analog of reinforcement in a continuous space? So you've been dealing with discrete spaces. So.
The answer is yes. I know that there exists, and I think it's a paper by Sabot, Tares, and Titus Lupu. They have. I know for sure, I can describe another model, the ones reinforced on Z. When you rescale it, it goes to a Brownian motion that is perturbed at its maximum. So if you reinforce just once and you use W equal to 1, 2x, you just reinforce once. When you rescale it, it goes to a Brownian motion that this is just in a 1-dimensional setting, that when it reaches the maximum is pushed somehow backwards. And then behaves like random walk on the range that has already been visited, but when it reaches a new maximum, goes a little bit, it's pushed. That's more or less. It's a paper by Burgess there. And actually, it is called by motion perturbed at its maximum.
Andrea, I wanted to ask if there is a criteria for which functions the random walk localizes and for which it does not localize.
So it depends on which random walk. For example, Vertex-Reinforced already localizes at a linear scenario. So let's look at edge and VRJP. For edge has been proved, edge reinforced, that this is the criteria. So you're summing, you look at the reinforcement function and you sum n going from 1 to infinity. This is fine. For this, it localizes. Okay. For vertex-reinforced jump process, I think the same holds, but I don't know. I think the same criteria is if and only if, but we were not able to prove it.
Okay, thank you, Andrea. Very nice talk. Thank you.
Thank you for question for coming.
Andrea, I have one question more. Say, if you look at some other types of problems, maybe your methods and approaches quite different to approach these problems. But say, if you look at problems where you first time reach something, some level or some area or whatever, do you know something about such things?
So each time you reach a new level?
No, the first time you reach something, for example, if you just consider...
You want to reinforce, or you...
So yeah, so with reinforcement, how it will be different to cases without reinforcement?
Well, there are processes where something is activated when you reach a site for the first time. And when you reach it for the second time, it behaves like simple random walk. And from then on, these are the so-called excited random walk. Mark Holmes had some nice paper on it. And we worked also with Minh and Kais on this. It's also called cookie random walk. Wherever you are on a site, you eat your cookie, and then you behave like a bit of a bias in one direction or the other. And once you are in a site without cookies, it's simple random walk. If this is what you are asking. From your expression, I don't think it's what you're asking.
Yeah, okay. Anyway.
But we can communicate maybe by email. I might have misunderstood the question.
Okay. Please, any other questions or comments? If not, thank you, Andrea, especially that you devoted your time before public holidays, just last minute. And okay, thank you very much.